My name is Ronnie Killo. I'm Director of Communications and Embedded Systems here at Southwest Research Institute. I've been here for 22 years. And as you can see from the video, the Institute's been around much longer than I have. Those are our humble beginnings. We started, as you saw, if you were listening in the video, that was a video from back in the 50s, I believe. It's funny, that voice was kind of popular back then in these documentary videos, and so it's kind of funny listening to that. I've had a great career here at the Institute, worked on a variety of projects. The Institute is a very diverse place, but I have to say that my favorite projects that I've worked on over the years have been in the space arena and flight software arena. And so it gives me great pleasure to have the Institute host this year's Flight Software Workshop, and so I want to welcome you here to San Antonio and Southwest Research Institute. Well, again, back to our humble beginnings. This was Southwest Research back in the late 40s and early 50s when the Institute was founded. I wanted to give you a little bit of an introduction to who we are in case you've never been to the Institute or don't know more about it, don't know much about us. We were started by the guy that you see in the upper left, a guy named Tom Slick. He was an eccentric visionary type guy, obviously with a name like Slick. He was in the oil business. And he had this great vision to start a scientific research and development organization to take technology that had been developed at that time during World War II and transition that into the post-wartime economy. And so he bought a ranch at that time, and this used to be called the Cable Ranch. It was an active working cattle ranch located at that time far outside of San Antonio. And the thought of buying a cattle ranch outside San Antonio in 1947 and starting a scientific research and development organization sounds like a great recipe for failure. But fortunately, I was not Tom Slick's advisor because, as you can see, his vision succeeded wildly. And we've now been around for 65 years, have over 3,200 staff, and are located on the same acreage that Tom Slick started the Institute on. And you see us there in the picture on the right. We've got 1,200 acres, over 2 million square feet of office and lab space, and 11 technical divisions. We are an independent and nonprofit research and development organization dedicated to the betterment of mankind through science and technology. You see our official mission statement up top, but I always like to say our real mission statement is we do fun work for food. And as I mentioned, I've been here for 22 years and have done a lot of fun work, and so it's a great place to be, and we're thankful that all of you are here today to engage with us in this discussion about the advancement of flight software in the space arena. As I mentioned, we do have 11 technical divisions, and so if you were to have the opportunity to walk around the grounds of the Institute, you would see a lot of buildings and a lot of labs covering just about every area in the physical sciences and engineering disciplines, and some of those are represented here on the slide before you, from autonomous vehicle research to aircraft, fire technology, chemistry, chemical engineering, geosciences studies. Just about everything you can think of is done somewhere at the Institute, and even being here as long as I have, I'm always learning something new that's going on at the Institute that I didn't know about before. One difference is we don't have cattle anymore. Instead, we have deer. When you drove in this morning, you might have had an opportunity to see some of those, but they don't let us hunt. So if you're a hunter, you know, you're not going to be able to do that. So that kind of gives you a little bit of a flavor of who we are at Southwest Research. If you have any questions about the Institute and what kind of organization we are, I'd be happy to answer those questions, or any of the others that are wearing Institute badges, I'm sure, would also be willing to answer those. I want to move on and give you a little bit of logistical information, though, for the workshop that we have ahead of us. Talk first of all about facilities. We have restrooms that are located really just on the other side of this wall here, so if you go out the doors at the back and around, you'll see men's and women's restrooms there in that hallway. Campus gates are going to be closing at 6:30 today, and so we need you to be off campus by 6:30. Particularly if you're a foreign participant, then you must have an Institute escort if you're leaving after 5 p.m. Badges must be worn at all times. I guess I'm already in violation here. I don't have mine on, but you need to have your badges on at all times, and please turn those in before leaving the workshop. If you have any general questions, we have Karen Downing and Lacey Johnston at the back. We have Allison Bertrand right up front, Kathy Ringel at the reception desk, and Melissa Van Hecky, who is our conference room manager extraordinaire, as well as our videographer at the back. One note on that, by the way, If you're a presenter, then when the presenter that is right before you is up talking, please go to the back to the videographer and he'll get you set up. We have to have 2 mics on, one for the audience here, one for the audience on WebEx, and so we have 2 sets of mics, and so we're going to be kind of alternating microphone sets in that way. So again, when you're about to be up to present, please go to the back and see the videographer and he'll get you mic'd up. Refreshments, we are going to have complimentary refreshments for you at the back during the morning and afternoon breaks, and so they're right outside the doors. I'm sure you've located those already, and so help yourself to that. Lunch for today and tomorrow will be at the Institute cafeteria or at local restaurants. I guess there's sufficient time to go around. If you need some help locating a local restaurant that's near enough for you, we can help you with that as well. And there's a list of those at the conference check-in. Friday we'll have box lunches brought in, and so if you have any special dietary restrictions, please let the receptionist know out front. Finally, dinner tonight at 7 p.m. at Casa Ria on the Riverwalk. Particularly if this is your first visit to San Antonio and Southwest Research Institute, you want to take advantage of this. It's a beautiful setting down on the Riverwalk. Great way to taste the flavor of San Antonio, both from a food perspective as well as the ambiance that we have on the Riverwalk. There's a lot of tourist attractions that sometimes are oversold, and this is one I can say that is never oversold. No one's ever disappointed. It's a beautiful area, and so I encourage you to join us there. It is $25 a person, and so see Karen Downing at the check-in desk if you haven't signed up for that. And then tomorrow night at 7 p.m. at Dave and Buster's is an informal gathering for people to get together and eat and have a good time. Please turn off cell phones. You know, I tell you, this has become a difficult problem with mobile devices and smartphones being as commonplace as they are. I sit in church now and hear cell phones going off constantly, and so please remember that and put your cell phones on vibrate or turn them off. If you haven't turned in your presentations already, please get those to Melissa. Give her a memory stick or a CD or email them or something to her. I don't think we have the email up there, but anyway, at this point, bring her a memory stick or something. So, also, you are supposed to sign a release form for your presentation, so if you haven't done that, please again see Karen Downing out front. Your moderator will introduce your presentation and remind you of your time limit. I did see a monitor up here that I think is going to have a timer on it, so you'll want to be mindful of that so that you can stay on time and so we can keep the workshop flowing. There are small microphones around the tables, the little gumstick size items in front of you that you can turn on for questions. Please just leave them in place and speak normally, and they should be able to pick up your voice just fine. And finally, I want to thank the workshop organizers. We have here at Southwest Research Institute, we have Robert Clark, Allison Bertrand, Scott Miller, Eddie Weigel, and Karen Downing. And with Johns Hopkins Applied Physics Lab, Andrew Harris and Chris, I'm not going to say that right. How do you say that? What is it? Croupiers, thank you. And from the Jet Propulsion Laboratory, we have, boy, you guys are really hurting me. Amale Ayaki, did I get that right? Close, thank you. And Aerospace Corporation, Dr. Ellen Unell. So anyway, thanks again to all the workshop organizers and sponsors and our exhibitors. We very much appreciate that. Can you tell the person online to mute their line, please? If there's somebody that's online, if you can mute your line, we're getting a little bit of feedback from you over here. So if you're online, please mute your line. Finally, I want to introduce our keynote speaker for today. Dr. Jim Burch is with us this morning, and of course, if you're in the space community, he's someone that needs no introduction. He's well known in the space community. He's been a PI on many experiments and missions, won many prestigious awards over his career, beginning in the military and then in the scientific community, and now here at Southwest Research Institute for many years. In 1997, Dr. Burch became the principal investigator of the imager for magnetosphere to Aurora Global Exploration. It was the first mission to study the Earth's magnetosphere from a satellite perspective. It was also the first NASA MidX mission and the first mission that was managed fully as a mission here at Southwest Research Institute. He's currently PI of a follow-on mission called the Magnetospheric Multiscale mission, which is also to study the Earth's magnetosphere. He is also the Magnetosphere's editor for Space Science Reviews, and in his spare time, he's vice president of Space Sciences and Engineering Division here at Southwest Research Institute. So help me welcome Dr. Jim Burch.
Hey, thanks, Ronnie. Good morning, everybody. Very pleased to be here. Thanks, Allison, for inviting me. Today I want to talk about these magnetic explosions in space that are things that you can see that are explosive. We find them almost everywhere, not only in space, but in the laboratory. A common thread. We figure they're caused by a phenomenon called magnetic reconnection. A lot of people haven't heard of it. Hopefully you'll know more about it after this talk. Fairly important, important enough that NASA has a major new mission. Well, it's not new anymore. It'll be launched in October 2014 that we've been working on here since 2005. And we're leading the science and the payload for it, and Goddard Space Flight Center is building the spacecraft. So the topics of the talk are magnetic reconnection and the magnetospheric multiscale, or the MMS mission. So things that you probably know about are solar flares and coronal mass ejections, that if you can look at the sun with instrumentation, X-rays, ultraviolet, you'll see these magnetic loops that form because of dynamo action in the convection zone just beneath the solar surface. These magnetic loops emerge from the surface, and because of magnetic reconnection, they get pinched off, forming coronal mass ejections that then flow out, caught up in the solar wind and flow out towards the Earth's magnetosphere, where magnetic reconnection occurs again. Over in this boundary region, these things carry a solar magnetic field, impacts the Earth's magnetic field, they interconnect, explosive phenomena occur, and the result is magnetic substorms, magnetic storms, and the auroral displays. This is an image taken from our image mission that Ronnie talked about that we flew here. It's an ultraviolet image of the aurora during a magnetic storm. So this is caused not directly by magnetic reconnection, but indirectly by magnetic reconnection. Now out in the universe, galactic jets, structures like this, people try to figure out what's causing that. Well, the most common explanation is magnetic reconnection that causes these plasmoids to form. Similar plasmoids are observed in the tail of the Earth's magnetosphere. Now there are these accretion disks surrounding black holes, and there was a theory back in 1979 that was similar to the sun. Now I didn't hit the laser, but I hit the advance. 1979, that you have this accretion disk similar to the sun. You have dynamo action producing magnetic loops, these magnetic loops emerging, pinching off, causing flares. And when this happens, magnetic energy is destroyed and converted to particle energy. And when that happens, there are emissions, in this case, X-ray emissions. This was the theory. Well, this is what's actually seen from X-ray astronomy satellite. This is a black hole at Sagittarius A at the center of the Milky Way. Now part of this video is real, like this. Part of it is an animation that's coming up showing the accretion disk rotating. Now this is animation based on data, but now this is real, and these are the flares, similar to solar flares that are emitted from that accretion disk. So this pretty much proves that theory. Suggestion is this is caused by magnetic reconnection. So throughout the universe, almost anywhere we look, you see evidence of magnetic reconnection. We know what it looks like, but we don't know what causes it. And that's where magnetospheric multiscale, or MMS mission, comes in. Now, one place you can study it directly is the Earth's magnetosphere. So here are solar magnetic field lines coming in with the solar wind, interacting with geomagnetic field lines. There's a region here in this box where reconnection occurs. We know that, so that's one of our targets for MMS. After this interconnection occurs, and in addition to the explosive phenomenon, because that's caused by the conversion of magnetic energy to particle energy, then these interconnected field lines are swept back by the solar wind. Eventually they have to reconnect again here so that the solar magnetic field can continue on, and these field lines are snapped back into the inner magnetosphere. So the other target for MMS is this box here. This is what we're after. Now similar to on the sun, here's a solar flare, similar reconnection. Trouble is it's very difficult, impossible to put a spacecraft there to measure it directly. And what guides our experiments for MMS, or has up until now, is the theory program. Simulations are run on big computers that show us what magnetic reconnection is supposed to look like. And this is what allowed us to design the mission, design the instruments. After we fly the mission, we'll have data that can then be put back into these models so that the tables are turned. And originally, the models helped the experiment. At the end, the experiment will help refine the models. Well, that's the plan. So now, in space, we want to know what causes reconnection, what drives it. Can't do anything about it. But in the laboratory, perhaps we can do something about it. This is from a Tokamak fusion machine. We have magnetic confinement fusion. Haven't been able to actually be put in operation yet, because every time you increase the electron temperature, that's what this is, you're increasing it and you want to increase it to the trigger point for fusion, then you have these crashes. It builds up again, crashes again. It's periodic, they're called Sawtooth crashes, and they're caused by magnetic reconnection. Down here you see the current density, reconnection rate. These lines here are magnetic field lines where they interconnect, reconnection rate goes up, and this crashes. Now it's possible from a mission like MMS, we may find out that if you inject certain types of species of ions, for example, in here, you may be able to cause this reconnection rate to diminish and this to continue. So the people in, for example, Princeton Plasma Physics Lab are very interested in MMS. We're working closely with them. We're hoping that we may find a practical application here. So now, what is magnetic reconnection? Probably got a pretty good idea by now. If you've got two regions here, you've got magnetic fields in opposite directions, down here and up on this other side. There has to be a plasma there, or nothing will happen. And if they come together, or pressed together, say by the solar wind and magnetospheric convection, something's making them come together, then there's this diffusion region. And that's where a magnetic field will be annihilated and converted to particle energy, where the magnetic field lines will link up, and then they will flow out in these jets. So we know about this diffusion region, we know how to find it, and we don't know what's going on inside there. That's the goal of MMS. So now, just to recap, we'd like to go out and study reconnection in black holes, supernova, and the solar atmosphere, Tokamaks, but we really can't do it here. Even at the Tokamaks, it's so small that all you can do is go measure the density and the temperature of the plasma. You can't measure the distribution function of the plasma or the electric and magnetic fields in it. So the only place we know of where you can do this experiment is in the boundary regions of the Earth's magnetosphere at its interface with the solar wind. And so this is what MMS is designed to do, but it's very difficult, because not only is this diffusion region small, it's also moving rapidly. And so we have to catch it. So we have this mystery, a lot of things we don't know about it right now. What produces the dissipation that goes on in this dissipation region or diffusion region? What determines this aspect ratio? See this rectangle? If these field lines if this was spread out more like this or was squeezed in closer, then this would either be fatter or thinner. And that determines the reconnection rate. And we know right now the reconnection rate is about 10%. About 10% of the magnetic field lines that come in, say from the sun and impact the Earth, go through this diffusion region, and the rest go around. And that's determined by the aspect ratio of this rectangle here. Also, the energy seems, especially in the magnetic tail of the Earth, the magnetic field builds up and builds up and builds up over a half an hour period or so. And then you have this explosive release. And so we don't know, as this builds up, what is the spark that causes reconnection to begin? And then what mechanism in here converts magnetic energy to particle energy? So these are the four-part mystery that we believe we can answer completely. So here again is our two targets, day side and night side of the magnetosphere. So as I mentioned, the mission was announced. We competed. We have a team called SMART, Solving Magnetospheric Acceleration, Reconnection, and Turbulence. We're about to get rid of that name because the mission is about to be renamed the Maxwell Reconnection region, and we didn't want to have Maxwell and SMART in the same. See, some of you are almost as old as I am. And So this launch, as I said, it's actually October 2014, recently been slipped. But this is the sun, this is the Earth, this is an actual image of the Earth in UV from the image satellite. Everything else in between here is invisible, but we have a pretty artistic guy here, and I said, well, I can't see a reconnection or these boundaries here, but if I could, I think this might be what it looked like. And so he drew this picture, and I went in and said, well, this, you know, not exactly what I had in mind. Why don't you change this and this and this? And I looked up and he said, you need to find another artist. So this is it, the first try. And so it's pretty good. There are 4 spacecraft here. And so this is what we've been using for a while now. So we have our objective to understand the microphysics of reconnection, specifically to determine the role of electron inertial effects and turbulent diffusion in driving reconnection. We want to determine the rate of reconnection, and that's that aspect ratio of that rectangle of the diffusion region I was talking about, and then also determine the ion effects. Now, a lot of the ion effects are known because of a previous mission called Cluster that was flown by the Europeans that flew in same regions, 4 spacecraft again, but the time resolution was such that they couldn't do much at all with the electron physics. But they did do a fairly good job of the ion physics, so that's part of the job's already done. And so this is the scale sizes that we have to work with. These are simulations. This is a MHD simulation of the magnetospheres, the Earth, magnetopause, the boundary between the magnetosphere, solar wind. Here's your diffusion region. If you look closer, 500 kilometer scale looks like this. Closer still, looks like this. Problem is, this is moving rapidly, 10 to 100 kilometers per second. You have to make measurements as this boundary moves by. And all of this turns out to mean, at least for electrons, we need to measure the whole sky in 30 milliseconds. On the cluster mission, they did the best job ever till now, 4 seconds. So we had to increase the state of the art by a factor of 100. And this is not only a hardware challenge, but it's also a data and therefore software challenge. I'll talk about it later. So here's one of these simulations. This is just the electron density plot here, magnetic field lines. And so it's a reconnection occurring, and this is the kind of thing that we're using to guide us in designing the experiment. Now this is the equation. Apologize for showing an equation, but if you're doing physics, you've got to have an equation. So here's the electric field, and this is velocity in the magnetic field. So if you didn't have reconnection going on, everything over here would be 0. So all you would have would be a motional electric field. You'd have plasma convecting around, no energy transfer. But these things can happen. First of all, if you have collisions, you have this dissipation over here. Don't have any collisions, forget that one. You have this Hall effect. This causes a differential motion between the ions and electrons, and it causes a current. And this current causes certain features in the magnetic field that have been predicted and observed by this European cluster mission. So they've done a pretty good job here investigating this Hall effect. So we know this much. This is where the action is, though, where the magnetic fields actually interconnect. Nothing's been done. There are different groups doing models. Some say it's a divergence of the electron pressure tensor. Some say it's electron inertial effects. But the importance of both of these is that they produce electric field components that are parallel to the magnetic field. And so the smoking gun for reconnection is you have an electric field, a magnetic field, and a current, all pointing in the same direction, and then you get dissipation and annihilation of magnetic fields. So that's what we're looking for. These two terms are the things that can cause it, and our satellites are designed to measure these pretty easily. So these are our physics targets. We have that as well as our spatial targets in the boundary regions. So this was every 10 years, the National Research Council does this study. This was the one from 10 years ago. They just finished a new one, but they had split this up into moderate scale missions and large missions. And for moderate scale, MMS came out to be the #1 priority. So we proposed it in 03, selected in 05, been working on it ever since. Of course, the moderate scale, well, it's $1 billion, so that's a large scale as far as I'm concerned, but at that time, thought it would be less. So we have 4 spacecraft, and if you drop one, then you've lost it, because if you had only 3, then you're investigating only a 2D phenomenon, because 3 points will determine a plane. So you've got to have 4, and there's a lot of different reasons. One is you've got these magnetic fields coming in and these jets flowing out. Here's the reconnection line. You've got to have satellites, at least sometimes, in the 2 inflow regions and the 2 outflow regions, so that you know you've got the diffusion region surrounded. And once you have it surrounded, you want to go inside, and this rectangle, or this diffusion region I was talking about, is actually two-scale structure. It's a larger scale, the turquoise, that's the ion diffusion region that Cluster's done a pretty good job on. But then the pink one is the electron diffusion region, the one that we need to study with MMS. And so we need to have these spacecraft clustered in these regions, in both of them. So we've done a lot of modeling of where we're going to see reconnection. Well, this one on the left is a view from the sun looking at the magnetosphere. So this is the dayside interaction region. And so the green is our orbits, and the red is when we're crossing the boundary. And then if you take a different view from above the North Pole, this time the sun's out to the left, and then you see places where we cross the boundary, and then places where we cross the nightside reconnection region. So we have to have 2 different orbits, one with a 12 Earth radii apogee, one with a 25 Earth radii apogee. And we have to have all of these instruments. One is built by us, the composition instrument. This fast plasma, this is the one that has to do the 30 millisecond electron measurements, built at Goddard. Johns Hopkins, energetic ion spectrometer, energetic particle detector from Aerospace, magnetometers, and electric field instruments, both led by University of New Hampshire with significant work from Colorado, UCLA, and then an Austrian contribution which maintains the spacecraft potential down at very low levels of a couple of volts, because without that, spacecraft would charge up and cut off the plasma you're trying to measure. And okay, so this is the one that says every 30 milliseconds and 250 milliseconds. So 30 is for electrons, the 250 is for ions. And so as I said before, the previous record was 4 seconds. And so this requires a lot of instruments, or we call this the first video plasma analyzer. On Cluster, they would have one instrument sweeping the energy as fast as possible and using the spin of the spacecraft to scan the sky. And that spin rate is limited because you have antennas out to measure the electric fields and magnetic fields, and so you can only spin so fast, and that's where the 4 seconds come in. So here we have a set of instruments that don't use the spin of the spacecraft. It's still spinning, but we don't care. So we have 8 electron sensors, 8 ion sensors, and we sweep their field of view electronically, and that way we can view the whole sky in 30 milliseconds for electrons, 250 milliseconds for ions. And most of these instruments are built and on the spacecraft. Some others are still in calibration, but we think it'll be just fine. Now we have a computer and data processor that serves the whole payload. So all of the instruments communicate with this central data processor, and then it provides the single interface to the spacecraft. And so we have to have a large memory because these instruments are operating very fast, so we can store data and create data very rapidly. But the downlink of data, for example, the S-band to DSN, it hasn't gotten any better since I've been in this business. It's always the same. So that's the choke point. And you have to do something. So we have here 96 gigabytes of onboard storage. That's 2 orbits worth of data. And then we can only get down to 4 gigabits per day. And so we have to select what data to bring down. Now we first wanted to do this prohibitively expensive and to get rad hard because of the high radiation environment. And so we had one guy in our group who had a pretty good idea, and that is to get flash drives, which aren't rad hard, or maybe they are. And so we went and put them in accelerators and did a lot of tests and found some that actually are rad hard. And there's some Samsung flash drives. Got a lot of these, 96 gigabytes worth. So it's pretty cheap, actually, and rad hard, even though they weren't designed to be. And this turned out to have been a pretty good line of business for us since we showed you could do that. So this is our payload. This is a pretty large payload deck. There are 4 of these. It's 13 feet in diameter. The inner part here is going to be filled up with fuel tanks because these have to maneuver around a lot. But here are the different scientific instruments. And now this was the concept, and now this is the first one all built up. And this was just very recently. And then this is when it was, here it is again, the payload deck. And this is the spacecraft system deck. So this is the observatory. All we have to do is put the fuel tanks inside here, put the solar arrays on the outside, and then this one's ready to go. 3 more that have to be built up. Look like this when they're stacked up to go in the Atlas. And so here's the problem I was talking about. We have a orbit, we have a region out here blue that we're interested in. This is the boundary region. And so when we get out here, we run all of our instruments at their fastest rate. In here, we don't care, we run them at a low rate. However, all this goes into that memory, but we can only selectively send down certain parts. That's these red parts. So we have to select these. 2% of the time is 74% of the data, and we have to pick the right intervals. And so we have 2 ways of doing that, talk about in a minute. But here's that downlink, 4 gigabits per day, or half a gigabyte per day we can get down. We have 96 gigabytes in memory. And so while we also, a job of the spacecraft people, and this is one of their software jobs, I have no idea how they're doing it, but they try to maintain a tetrahedron configuration, like a pyramid. And that's, you think of having a satellite at the origin, and one along X, and one along minus X. And or one along X, Y, and Z. Origin, X, Y, and Z, you have a pyramid, and then you can get spatial gradients of all the phenomena that you're measuring. So the scale size on the, keep hitting this thing. Now I'm in trouble. Okay. Okay, the scale size is different on the day side, 10 to 160 kilometers. On the night side, it's 30 to 400 kilometers. So we try to maintain these configurations, but as they get closer to the Earth or for lunar perturbations or whatever, these things start to deteriorate like this, and so they have to be moved to maintain this 80% perfect pyramid throughout that region of interest. That's a requirement. The other requirement is that they don't collide. Okay, so here's the simulation, what it looks like. See in a minute, you'll see, well, there's the Earth, magnetic field lines. This will turn into 4 spacecraft in a minute. So we're trying to maintain this pyramid configuration. And it wants to go into a line when it gets close to the Earth, but as it gets out to the region of interest, you have this pyramid configuration. And so that's the job of the navigation team. And seems good. We get the position down with GPS down when it's close to the Earth, and then we propagate that out. So here's the idea of the sequence of events. Phase 0, we're commissioning instruments, no science. Here's the day side. Here's noon right here. It's midnight, dawn, and dusk. So we launch pretty much equatorial precession around this way. We're commissioning the instruments. Then we scan through the day side here once. And then we're going to do it again, so we come back through the night side. We don't do anything here because it's too close to the Earth. And then we scan the day side again, and then we pump up the orbit, the 25 Earth radii, and then we scan through the night side. And that's 2 years, and that's the mission. So a lot goes on during each of these orbits. A lot of things having to do with, well, you get the position with GPS down here close to the Earth, and you do certain maneuvers to maintain this pyramid configuration. Our main data taking is in this blue region. And then here's our downlink. And so it's a pretty busy time. And this is about a 1-day orbit on the day side. By the time it gets to the night side, it's more like 3 days. So we have 2 ways, as I mentioned a while ago, we have 2 ways of identifying what data to send down. The first is our onboard assessment of data quality. And we have that all pretty well developed. When we started, that was the only thing we were going to do, but then we had some doubts about how smart it could be. And so we have another method of selecting on the ground. And that's why we have 2 orbits worth of data in storage. So as we get data down, we get the burst data that was selected on board, and we get summary data of everything else, and we can look at that summary data, and for the next downlink, we can change what's going on in the spacecraft and say this interval, even though we can't see the high rate data, it looks like it's more interesting because it crossed a boundary or something, and so we can change what's happening. And all of this here involves a lot of software on the ground, and this involves a lot of flight software on board. Could be we keep doing both of these for 2 years, or it could be that we decide one or the other is better. And when the onboard quality indexes involve things like electric fields parallel to the magnetic field I was talking about, variation in particle flux, large magnetic field variations, high fluxes of energetic particles, things like this. All the instruments send in, and if they all say this is good, that's fine. Then it comes on the ground, and we combine the data from the 4 spacecraft, and all the 4 spacecraft say it's good. Then we've got a very high index for sending that data down. So that's the way that works. Already talked about this. This also shows, again, these onboard triggers. And we have a lot of these. If I showed the whole list, it would be several slides, but it's all pretty much hard-coded into FPGAs and stuff. And then we have the scientist in the loop that can change or veto the priorities that are set on board. And so that's it. That's a summary of MMS. We're going after reconnection to understand what causes it, how it works, and we think we'll have a definitive experiment. And right now we're working on our second payload integration up at Goddard, and we'll be launching in about 2 years from, a little less than 2 years from right now. So thank you. If you have any questions, I'll try to answer. If they have anything to do with software, I'll defer to Allison, Robert, or Ronnie. Okay.
Any questions? So let's thank our speaker.